Good. So thank you for coming. And let me open up today's sessions with a talk about our advanced threat detection technology and an interchange of security intelligence through the STIX and TAXII format. So we're going to talk about an integration API. But before that, let me give an introduction to the advanced threat topic here. Before I go further, two questions. How many of you are familiar, have heard of the Cisco Cloud Web Security Service, the web security proxy in the cloud? Anyone? Just for me to understand how much I should introduce the concept. So I will introduce. And then how many of you have heard or worked with the STIX or TAXII API? Anybody manages a SIEM in your environments? Splunk, ArcSight? Good. So that will be a relevant topic. So that is a common API that we use to integrate with SIEM type of solutions. Good. Let's get started. So some background on advanced threat in general. When we talk to our customers and we discuss advanced threat, they're talking about couple changes in the reality where they operate. So number one, there are threats that are going to get in, and they are learning to live within that environment. So if you have a breach inside your organization, what do you do next? How do you look for a breach device? And then number two, surprisingly, so surprising or not, most of them will agree that advanced threats are generally going to get inside their organization through an infected email. As simple as that. A human being will click on an infected attachment. And finally, and this is backed up by our internal threat research and additional industry research, the most common command and control channel for advanced threat is actually the web. Why? The threats will know that web is usually the open channel. So that's why they're gonna leverage that, try and leverage that. So this is why it makes so much sense to apply additional analytics onto the web traffic to discover threats that are already inside the network. And so this is exactly the topic that I'm going to talk about. I'm going to talk about a specific technology called cognitive threat analytics, which I am a product manager of. And also, I'd like to make this an interactive session. So whenever you have any questions, please shout. There's not too many in the room right now, so I think we will have time to get through questions already, and then I'll take additional at the end of the session. So if you look at and I will talk about cognitive threat analytics within the context of web security industry. So if you're looking at web security historically, the entire industry has been focused on protecting the before phase of an attack and a during phase of an attack. What I'm showing up here is a model, security model that we use across of Cisco security that talks about the three phases of an attack life cycle. So what's happening before an attack, during an attack, and after an attack. And what we're introducing as a new concept is the necessity to actually operate actively in the after phase. So we're exactly working in this new reality where threats may get in, and you need to be actively looking for them. And we have dedicated technology in that area called the cognitive threat analytics, where we focus on analyzing the telemetry of the network communication, looking for symptoms, characteristics of communication, working with the web access logs as input data to our analysis. And what I'll introduce is the details of the processing engine that we use, the details of the detection that will allow us to identify infected devices inside the network. And then I'm going to talk about how we then expose that information through an API for machine processing in the security workflows of organizations. So let me start by, again, reiterating the security model of the before, during, and after phase of an attack continuum, but going deeper into exact technologies that we're applying in the different phases. So this is actually a mapping of the before, during, after model over to our cloud web security premium service offering. So that is a web security proxy that sits in the cloud. You can redirect your traffic from individual devices or the network choke points into the cloud so that your web traffic will get filtered, IP reputations applied. So in the before phase, we're using pre-existing security intelligence to block requests that are just inherently bad and they shouldn't even go out of your environment. And then when the requests actually leave your environment, this is when we're transitioning into the during phase of the processing. And we see a response from the destination server coming back. And there is going to be, again, a series of checks that we're going to apply to decide, is that a legitimate traffic or is that malicious, an attempt to deliver bad payload inside your organization, and then we're going to block that or analyze that further. So we have, again, a portfolio of technologies, traditional technologies from the cloud web security space, applying anti-malware engines, outbreak intelligence, which is a heuristics-based engine to identify zero-day attacks, and then an addition in the advanced threat space, a technology called AMP from SourceFire that's pivoting on file reputation. So we're going to inspect payload, files that are passing through the perimeter, anything known bad, so matching against a knowledge base of over 1 billion samples, we're going to block right there if it's known bad. If it's an unknown artifact, so a new payload that is specific to your environment, we're going to send that off to more detailed analysis. We're going to do file analysis, and that is already transitioning us into the after phase. So artifacts that are new, we're going to inspect them continuously over time. We'll go back to them repetitively. And if we find them malicious, at a later point in time, we're going to alert you retrospectively of what happened. There's been a file that is now convicted as malicious that got inside the organization. Now, next to that, we do have the CTA technology, cognitive threat analytics, that is looking purely at behaviors operating in the after phase. So looking at behaviors of individual users on the network, modeling every single user's activity within the context of the entire network, looking for symptoms of this user is no longer a human being behind their web browser. It is actually an infected machine that's establishing command and control communication. Now, the beautiful thing is that if you apply an anomaly detection technology, which it is, in the after phase, you're providing protection and capability to discover any threats that are already there inside the network. So they could have penetrated the environment entirely bypassing the web as an infection vector. So all the before and during phase processing is there to block additional bad payload coming in. But if that payload came in through email, infected USB stick, or people roaming in and out of the organization, and you now face the situation of an infected device, this is where you need additional visibility and analytics in now the form of reviewing the web logs to identify you of the fact that someone inside the network is already infected. So CTA is a breach detection technology. And what I'll do now, I'll walk you through the details of the detection engine. It's backed up by 10 years of research, a spin-off from university research originally, and research projects funded by US Army and US Navy. And then the technology spun off into a technology company called Cognitive Security that got acquired by Cisco in 2013. So this detection engine, as much as any other anomaly detection engine that you are thinking about, is going to try and optimize against two competing criteria. On one hand, you want to discover just anything bad, anomalous, malicious that is out there on the network. And at the same time, you want to make sure that all the alerts that you're going to finally present, they're going to be very, very precise. And so in order to optimize for both of these criteria, this is why we use a layered processing engine. There's not a single algorithm that would give you both. So we're actually applying a series of techniques from the domain of statistical machine learning, artificial intelligence, ensemble classification, to actually crack through the problem of, on one hand, identifying anything that's suspicious, and then narrowing down the search into things that are truly malicious and pose a very concrete risk on the network. So we go through 3 processing layers, and each one of them has a distinct meaning. So at the beginning, we're operating with individual web request artifacts. So we see the web logs, so the information of source IP, destination IP, timestamps, volumes of data, process, etc. So telemetry information. And in this first layer, we're very much focused on anomaly, on individual web request basis. And as we move forward into layer 2, we're going to build a notion of malicious events on the network. That is a series of requests that are coherent together, and they actually represent a specific threat activity. Could be an attempt to establish command and control, could be an attempt to exfiltrate data, and so on. And finally, in the third layer of processing, we actually operate with the notion of a threat for an individual device. So we're collecting observables, individual malicious events, and when they come together in a particular configuration exceeding certain threshold, this is when we're actually going to convict a device and create an incident for them. And we're then further going to contextualize an individual threat infection for individual user and map that across perhaps multiple users that we see globally to also map out the entire threat infrastructure that we're discovering. What we talk about here are predominantly novel, emerging, or morphing threats that are by large undetected by the traditional endpoint security. So this is where, this is why, number one, we are identifying the command and control, because on that endpoint, the threat did not get discovered and eliminated. Going into the details of the individual processing steps, and just to maybe go back and emphasize the sort of the processing scale that we have, we're operating around 10 billion web requests on daily basis in our production environment, generating at the end thousands of individual alerts on daily basis. So you can imagine the amount of processing power that is required and the amount of logic, processing logic that is behind the engine. So we really deal with a true big data problem there. Number one, in layer 1, we are first working with individual anomaly detectors, where we apply 40+ detectors to form a detection ensemble. You can think of that as a jury system in the US. You have a jury, individuals that are going to vote guilty or not guilty. And then you're going to apply their collective vote, assuming that if one of them makes a mistake, so classifying false positive, false negative, the other ones are going to make up for that, being independent, giving an independent judgment. So what we have are 40+ independent detectors that are working together, and they're going to take a decision on every individual web request basis. So you're going to see the requests coming in through the initial layer of processing. For each one of the requests, there is going to be a vote. Is it anomalous? Is that unknown behavior, or is that normal behavior? And finally, all these are going to add up together to give a one assessment for every individual web request. Now we're further going to take that and stabilize the assessment of the overall network behavior, because this is what we're building out here. It's behaviors of individual users, but also of the entire network overall. So we're going to stabilize that over time in a processing step that we call the trust modeling, where we're going to aggregate similar requests together, and over time we're going to form an overall judgment on an entire space of requests. So certain group of requests we're going to identify as normal behaviors, unknown, or anomalous. Now this is end of the layer 1. We have made a decision on what is the normal part of the traffic, so modeling every individual network's behaviors separately from anybody else. And we've made a decision on what is the normal behavior and what is statistically anomalous. So to give you an idea, it is going to be roughly around a 1% of the traffic that will go further into the next processing layers. where we take the most anomalous part of the traffic, and we're going to classify that further to put that further into the into actual alerts. So in our layer 2, we're going to take things that have been identified as anomalous or unknown, and we're going to bucketize them. We're going to classify them into recognized buckets of behaviors or activities on the network. We're going to recognize normal or legitimate activities. We're going to recognize malicious activities that are going to be the seed of creating an incident for an individual user. And we're then going to identify unknown activities that are going to act as suspicious behaviors that are going to form context, additional context of a malicious activity of a user. Going further, we are going to attach these anomalous and malicious activities to individual users, and we're going to collect them over time. And as more evidence is becoming available, we're going to be able to convict more devices of actually carrying a threat infection. Again, we're talking about threats that are emerging, novel, unseen before. Detection made purely based on statistical machine learning and statistical modeling. In the final layer of processing, we're going to take the detection of individual users that are identified as carrying an infection, and we're going to correlate their behaviors within the same organization and also symptoms of the infections. We're going to also correlate on a global scale. So that will eventually allow us to pull together an entire view of a threat campaign that we're seeing across multiple individual users. So there's going to be a few correlation activities that we're doing. So first on the local level within an individual network, then on the global scale, so behavioral similarity of the malicious activities that we've identified for an individual. And then we're going to also extrapolate on the threat infrastructure that we see common between different incidents. At the end of this processing step, we have identified threat campaigns that we're then going to present in form of a report with additional security intelligence that we have collected internally across all of Cisco. And we're going to present threat campaigns with a risk level confidence 100%. These are infections with 100% certainty. And finally, let me show an example of how that processing would work. So you do have a user that is pushing their traffic through Cloud Web Security as a proxy. There are multiple channels here depicted that are going out to multiple domains, and there are behavioral indicators on the pieces of communication. So either an attempt to establish a communication to a domain through domain generation algorithms, an attempt to establish a command and control activity, additional context of did the activity get blocked in the previous processing steps of the CWS or not, to finally identify 2 active command and control channels. So we're actually, when we present reports, we're going to say there is an individual that is infected, and this is the exact command and control infrastructure that we're mapping out for that device. And these are the active channels that you need to worry about, you need to mitigate. At the end of the day, the remediation for these infections is actually going to be, you need to go to the endpoint to clear the infection there at the endpoint. Any blocking that you do at the web perimeter level is only going to be a workaround of the situation that there is an advanced threat sitting inside the environment, posing a risk or causing damage that you need to get rid of at the endpoint. Again, a reiteration of there are 4 processing steps, and we are moving across the detection of anomalous activities over to malicious events, over to actual threat incidents. And finally, let me give you a couple examples here. So when we present results, we're going to present them in two forms. Number one is going to be detections that have been done for individuals, but then pulled into a wider context of an entire threat campaign that is spanning one or more users. And this is when we're going to present them as confirmed threats. The fact that we have made the same detection on multiple individuals independently, because we do start from different original conditions in every single case, is actually going to allow us to pull up the overall confidence on the detection to 100%. So this is why these detections that are done on more than a single user are confirmed and high precision, high confidence findings. We're going to present them in form of a report that gives you, and I'll show you another example that is actually easier to read, but this is just the overall structure. We're presenting a risk level, confidence, identity of the threat campaign, how many users are affected within your organization, and then what is the global footprint of that threat? Is it a narrow-focused, perhaps targeted attack, or is that something that is more widespread? That's obviously going to drive your remediation action from that finding. And we also provide additional context from the rest of the portfolio. So we're making a genuine new detection and discovery with the cognitive analytics engine, statistical modeling engine. But then for the users that we have discovered as carrying an infection, we're going to pull in a context of what we believe has happened on the endpoint. And we're going to pivot on a threat samples database within our AMP threat grid solution. We're going to take samples that from the network perspective behave similar to that threat that we've identified within the network. And we're going to give you endpoint behaviors that we suspect that threat has done on the endpoint. So we're going to give you a list of executables that would have been touched by threats that behave similar from the network perspective. So if you decide to run forensics, you need to run forensics on the endpoint. We're going to give you hints on what actually happened. And then the other category that we present are detected threats that are identified for individual users. So that means that may actually be targeted at an individual. So not to be underrated, underestimated. We want security analysts to pay attention to these detections. They are generally going to be below 100% confidence, say 90-95% confidence. But for organizations whose threat tolerance is very, very low, they really want to deal with these types of detections because they really pose the higher risk of being targeted with an attack. And then for these detections, we're actually going to map out an entire command and control activity that we have identified for the individual detection. And this is the overall processing, moving from the anomaly detection into trust modeling, classifying individual behaviors into malicious activities to finally deliver incidents for individuals pulled into a threat campaign or separately. And finally, one example here, so a detection that we've done on a network identifying consistent command and control activity where the customer tries to confirm that with endpoint security, and they are running endpoint scans and can't confirm any malicious artifacts. It takes a week until they actually discover a threat, and then they think they have remediated that threat, where in fact they have only removed a component of a multi-component threat on the surface. And so they see a reappearing pattern of more threat artifacts popping up on the endpoint, where we're telling them from the very beginning, well, this is a rootkit-capable threat that is going to deeply rooted into the operating system. You're never going to be successful removing that with your endpoint security tools that in the first place haven't been able to identify that. So the proper solution to resolve these threats is actually going to be a re-image in vast majority of cases where the risk level is above certain threshold, so say 8 out of 10, and the confidence is at least 90%. This is where we see customers actually re-imaging. And they're going to use, so just a summary of that would have been a Zeus Trojan variant of a threat, a novel variation, emerging variation of that threat that eventually has the capability to deliver a ransomware. example of what that individual command and control activity looked like for that particular user, and an example of in most cases, the actual command and control activity is going to be encoded or encrypted type of communication that has the capability to carry instructions to command and control, exfiltrate data, deliver additional payload, etc. And now this is what that user interface and report would look like. So again, summary of the risk level, confidence on that threat, local and global context of that threat, full description of what is the real behavior of that threat and what is the recommended next step. Again, in most cases, a reimage, and a summary of how many users affected locally, etc. And finally, we're getting over to the STIX TAXII API. So this is actually a standard that is getting quite a lot of adoption across the industry because it's a really brilliant language to allow you to talk about security intelligence in a hierarchical fashion. So it allows us to talk about, we have discovered a threat campaign. Within that threat campaign, we have a number of individuals affected. And for these individuals, we have discovered these particular observables. We do have pre-integration with Splunk, with ArcSight, QRadar actually using the same methodology as ArcSight, the Ceph format, working on Logpoint, and actually anybody who implements STIX TAXII API will be able to integrate. This is the format for the STIX language. So again, you're providing hierarchical information from threat campaign over to individual affected users and individual observables. And finally, a brief example of it is an XML formatted output. Now, what we provide on our side, we have made a sample client for the TAXII API available on GitHub, and I can provide links to anybody who's interested here with also installation instructions. And now the most important is we do provide STIX formatted output as a standard. But if you do not have native support for STIX, we also provide translation tables to other formats. So for instance, for ArcSight, for QRadar integration, we do translate to a CEF, the Ceph format, which is the native format for these SIEM environments. So what you can then do with the API is you're going to automate the processing of threats that have been discovered into the remediation flows of the security operations center. So that was my introduction of the behavioral breach detection technology and the STIX TAXII API. I'm available for any questions, anything related advanced threat or STIX TAXII. I'll leave it up here. Good? Helpful? Any questions, anything? Good. Thank you very much.